Alright, let's begin by talking about one of the most essential areas in electrical engineering, high voltage engineering. Now, you might be wondering, why do we even need to study this separately? After all, electricity is electricity, right? Well, the moment you start working with large-scale power systems, things get a bit more complex. When you are dealing with a small battery or a simple household circuit, voltage levels are low and risks are manageable. But when we move on to generation, transmission and distribution of electricity of a national or global scale, you are talking about hundreds of megawatts of power traveling hundreds or even thousands of kilometers. That's why high voltage comes in. Using high voltage allows us to transmit power more efficiently with less energy lost as heat in the wires. It's a principle that underpins our entire electrical infrastructure. Think about it. The electricity that powers your home might have started at a generator hundreds of kilometers away. Without high voltage, that power wouldn't have made it to your neighborhood intact. So, in this topic, high voltage engineering will look at all the specialized knowledge needed to work safely and effectively with high voltage systems. That includes understanding insulation requirements, how electrical fields behave under high stress, what happens during lighting strikes or switching surge, and how to test and protect the equipment we rely on. It's not just about the numbers or voltage ratings, it's about knowing how to handle massive energy flows in a controlled, reliable and safe way. And that's exactly what we'll be exploring today. Let's start with a basic but powerful idea. Energy cannot be created or destroyed, it can only change forms. That's the principle we use every day in electrical engineering. When we generate electricity in a power plant, we are really just converting mechanical energy from steam turbines, water flow or wind into electrical energy. Now, once that energy is generated, it has to go through three main stages before it reaches your home or industry, that is generation, transmission and distribution. Each of these stages has its own technical challenges, and one of the biggest is maintaining a constant balance between how much power is being produced, how much is being demanded by customers, and how efficiently it's being delivered. This balance isn't automatic. It requires continuous monitoring, regulation, and control. For example, if demand suddenly spikes but generation doesn't catch up quickly, the system could experience instability or even fail. That's why modern grids use automation and control centers to respond in real time. Now, speaking of generation, the voltage level at which power is generated depends on the size of the generator. A generator with 200 megawatt capacity typically produces electricity at around 11 kilovolts, while large generators in the range of 500 to 650 megawatt generate at 22 kilovolts. These voltages may sound high, but for transmission over long distance, they are still not enough. So, we use step-up transformers to raise the voltage further, minimizing losses during transmission. And here's a point I want to emphasize. Higher power doesn't necessarily mean higher generation voltage, but rather, as power level increase, we choose generation voltages that balance equipment size, insulation requirements, and efficiency. Or to put it another way, we don't generate at very high voltage directly, we generate at moderate levels are the practical for machines. And then step them up for long distance transmission. That's one of the first lessons in high voltage engineering. Understanding not just what voltages are, but why they are chosen that way. This image illustrates the complex flow of electrical power from generation all the way to the users, and it's broken into four main stages, that is generation, transmission, sub-transmission and distribution. At the top of the image, we can see a real-world layout showing how electricity moves across the power system. At the bottom, there is a single line diagram or one-line diagram, which is a simplified electrical representation that engineers use to design one and understand complex systems. At first, the generation, 13,200 volts. It all starts at the generating station where electricity is produced, typically by rotating machines like turbines in thermal, hydro or nuclear plants. The voltage here is usually around 13.2 kV or 13,200 volts, which is too low for long distance transmission. That's why the power is first sent through a transformer in a transmission substation to increase the voltage to a much higher level. This process is called stepping up the voltage. In the next stage, the transmission. Now the power is at a much higher voltage, often around 345 kV, that is 3,45,000 volts, which makes it efficient to send across the long distance transmission lines. High voltage is essential here because it reduces the current and therefore minimizes I²R losses or energy lost as heat. These transmission lines carry bulk power over hundreds of kilometers to different parts of the grid. At the end of this stage, another transmission substation steps up the voltage down slightly for the next level. In the next stage, sub-transmission. This stage delivers electricity from the main grid to industrial zone or urban substations. The voltage here is usually around 69 kV, which is still high but more manageable for local systems. The power is distributed to industrial customers directly or passed on to distribution substation where the voltage is again stepped down to a safer level. At the last stage, distribution. 13,200 volts or lower. Finally, we reach the distribution stage where the voltage is brought down once more, typically to 13.2 kV or even lower depending on the region and application. This power is then sent through distribution transformers to the residential, commercial or small industrial customers. This is the electricity that finally powers our light, refrigerators, factories and everything else we use in our everyday life. Now let's talk about high voltage engineering in a way that makes sense beyond just definition. This is a specialized area within electrical engineering that deals with system operating at voltages much higher than what we encounter in our homes or small-scale devices. We are talking about hundreds of kilovolts used in a national grids, industrial plants and transmission system. At its core, high voltage engineering is concerned with how to plan, operate and test equipments like insulators, circuit breakers, transformers and surge arresters, all of which are designed to function reliably under extreme electrical stress. But one of the most critical parts of this field is something called insulation coordination. What does that mean? It's about making sure that every component in a high voltage system has the right kind of insulation to handle the maximum voltage stress it might experience, both during normal operation and in rare events like lightning arrestor or sudden fault. In other words, it's about matching the electrical strength of the insulation with the worst-case electrical conditions it might face. You can say insulation coordination is just like designing a seat belt. It has to be strong enough to protect you, not just during a calm ride, but in the event of a crash. That's how high voltage engineers think, not just about what usually happens, but about what could go wrong and how to prevent failure when it does. Ultimately, high voltage engineering plays a foundational role in ensuring that large-scale power systems like national grids can operate safely, reliably, and over long distance, even when exposed to severe environmental and electrical stress. And just to emphasize this, again in a different way, without the principles and tools provided by high voltage engineering, our power infrastructure would be too fragile to support modern society. It's what gives the entire system its backbone and resilience. When we talk about the present structure of the power sector in Bangladesh, it's important to understand that it is organized in a layered and functional way where different entities play very significant or specific roles. Starting from policy making at the top all the way down to electricity generation, regulation and delivery. At the apex of this structure is the Power Division under the Ministry of Power, Energy and Mineral Resource, or in short MPEMR. This division is responsible for setting the overall direction, long-term planning and energy policies of the country. Think of it as the central authority that coordinates national level decisions and goals for the entire power sector. Then comes the regulatory body, which is the Bangladesh Energy Regulatory Commissions. Bangladesh Energy Regulatory Commissions acts like a referee. It does not generate or distribute electricity itself, but it oversees and regulates activities across the sector. It sets tariff structure, ensures compliance with technical and safety standards, and tries to make sure the power system remains fair, transparent, and financially viable. Below the regulatory layer, we have the generation entities, and this is where actually electricity is produced. The Bangladesh Power Development Board, or BPDP, is the key public sector player here. It's the largest and oldest body involved in electricity generation. But BPDP isn't alone anymore. Over time, several other generation companies have emerged, including Ashuganj Power Station Company Limited, Electricity Generation Company of Bangladesh (EGCB), and Northwest Power Generation Company Limited. These are typically state-owned but operate more like corporate entities with some operational independence. In addition to this, the sector also includes independent power producers. These are private companies that generate electricity and sell it to national grid. And here's an important point I want to emphasize. Electricity generation in Bangladesh is no longer the responsibility of a single organization. It's now a collaborative system where public and private generators work side by side to meet the growing demand for power. Or to put it another way, the generation landscape has diversified, with multiple players involved to improve efficiency, increase capacity, and reduce dependency on any other institution. This structural shift has been essential for handling the rapid growth in demand, enhancing reliability and encouraging investment in new technologies. This diagram gives us a good overview of how the power sector in Bangladesh is currently structured, and it helps us understand who does what in the broader system of electricity generation, regulation and distribution. At the very top, we have the Ministry of Power, Energy and Mineral Resources. This is the central authority that oversees all energy-related activities in the country. This ministry is divided into two wings. That is, the Energy and Mineral Resource Division, which mainly handles fields like gas and coal, and the Power Division, which is focused especially on electricity. The Power Division is supported by a specialized technical branch called Power Cell, which helps with planning and policy implementation. Beside them, we have BERC, that is the Bangladesh Energy Regulatory Commission, which acts like as the independent regulator. BERC doesn't generate or supply power, but it oversees the entire sector, ensuring fair pricing, technical standards, and consumer protection. Moving down, we will see the main operational bodies, that is BPDB, Bangladesh Power Development Board, is the core government institution responsible for power generation and also involved in some transmission and distribution. BPDB oversees several state-owned generation companies like PGCB for transmission, APSCL, EGCB, NWPGCL and WZPDCL, and it also works with independent power producers, IPPs, which are private companies generating electricity and selling it to grid. Alongside BPDB, there are another major players such as REP, Rural Electrification Board, which focuses on delivering electricity to rural areas, and companies like DPDC and DESCO, which are responsible for distribution in urban areas like Dhaka. Under REP, we have PBS, that is Polli Bidyut Samiti, and Rural Power Company Limited, which implement and manage power delivery at the grassroots level. One thing to emphasize here is that the structure is multi-layered and collaborative. No single agency does everything. Instead, roles are divided to allow for better focus, specialization, and efficiency. Or to put it another way, the power sector in Bangladesh operates like a coordinated network of government bodies, state-owned companies, and private entities, all working under a central policy umbrella to keep electricity flowing across the country. This structure has been key in expanding access, managing generation capacity, and handling the increasing complexity of national power demands. In the structure of Bangladesh power sector, once electricity is generated, it has to be transmitted efficiently across long distance before being distributed to homes, business, and industries. And this entire process is managed by specialized entities. The responsibility for transmission lies entirely with the Power Grid Company of Bangladesh, that is PGCB. PGCB is the sole authority that operates and maintains the high voltage transmission network, typically handling voltage of 132 kV and above. Their job is to move bulk electricity from generation stations to various substations across the country. This part of the power system is crucial because without a strong and stable transmission backbone, the rest of the supply chain can't function properly. You can think of PGCB as the national highway system for electricity. It doesn't generate or deliver power to your house, but it carries massive volumes of electricity to the regions where it's needed. Now, once the electricity reaches local substations, it needs to be stepped down in voltage and delivered to consumers. This is where the distribution companies come in. There are several distribution companies that handles different regions, that is BPDB, Bangladesh Power Development Boards, handle the distribution in many parts of the country, especially in areas not yet handled over two separate entities. Then there's Dhaka Power Distribution Company and Dhaka Electric Supply Company Limited, which manage electricity distribution in different zones within Dhaka city. For the southwestern part of the country, distribution is managed by West Zone Power Distribution Company. One thing is to highlight here is that distribution is regionally divided to improve management, accountability, and efficiency. Instead of one big organization doing everything, each company focuses on a specific zone. Or to put it differently, distribution is intentionally decentralized, allowing each company to tailor services, respond to local demand, and maintain infrastructure more effectively within their area. This division of roles between transmission and distribution is the key to ensuring that power flows seamlessly from power plants all the way to end users, without unnecessary delays, technical losses, or administrative bottlenecks. In every modern country that relies on electricity for lighting, industrial process, or household use, there exists a structured system of transmission and distribution to move electricity from where it's generated to where it's needed. When power is generated, whether form of a thermal plant, hydrostation, or renewable resource, it can't be used immediately at that voltage level or location. Instead, it has to be delivered over long distance to cities, factories, and homes. This is where electrical transmission comes in. Transmission involves moving high voltage electricity over hundreds of kilometers using large towers and transmission lines to reduce losses and maintain efficiency. The high voltage allows electricity to travel further without wasting too much energy as heat. Once this power reaches a populated area, the voltage is stepped down at substations and it enters the distribution system, which then delivers electricity at much lower voltage to individual consumers. One key idea here is that transmission and distribution are two separate stages in the journey of electricity. One focuses on moving bulk power efficiently across distance, while the other ensures that the power is delivered safely and reliably to end users. Or put another way, transmission is about covering distance with minimal loss, and distribution is about reaching people with usable safe voltage levels. These systems working together form the invisible backbone of modern civilization, allowing us to power everything from hospitals to smartphones without ever really thinking about how that energy got there. In the structure of electric power supply, once electricity has been transmitted over long distance at very high voltage like 132, 66 kV or 33 kV, it needs to be stepped down to more manageable levels for practical use. And this is where primary and secondary distribution come into play. At the primary distribution stage, the transmission voltage is reduced to 11 kV at a substation using step-down transformers. This 11 kV power is then supplied to large commercial and industrial consumers such as factories, manufacturing plants, or large-scale commercial operations, which have high energy demands. These heavy consumers typically set up their own substations to receive, control, and utilize this high voltage electricity efficiently. They receive it through three-phase, three-wire overhead system that carry the 11 kV supply directly to their facilities. After that comes the secondary distribution stage, where the remaining 11 kV electricity not used by industrial consumers is sent to a smaller substation located near residential or urban areas. Here, the voltage is further reduced, typically to 440 volts, using additional step-down transformers. This lower voltage supply is what powers homes, shops, schools, and other everyday establishments. So, to reinforce one important idea, primary distribution is meant for delivering moderately high voltage electricity to large consumers, while secondary distribution is focused on stepping it down to safe and usable levels for the general public. Or to say differently, primary handles big loads at 11 kV for industries, and secondary makes that electricity usable for household and smaller facilities by reducing it to 440 volt. These two layers work together to ensure that every type of consumer, from large factories to individual households, get the right amount and voltage of power tailored to their needs. The operation of transmission and distribution system in a power grid isn't just about flipping a switch and keeping the lights on. It involves a complex sequence of planning, monitoring, decision-making, and post-analysis that unfolds across different time scales. These time scales reflect how far in advance we are looking and what type of operational decisions are being made. The first stage is called the operational planning phase, and it can start several years in advance, going all the way up to a few days before actual operation. This is when utilities and grid operators focus future demand, plan maintenance schedule, assess generation availability, and make strategic decisions about how the grid will be managed. After that comes the extended real-time operation phase, which usually ranges from a few days ahead up to a few hours before the actual delivery of electricity. This stage is all about refining those earlier plans based on the updated weather-focused field availability or unexpected outage. Then we move into the real-time operation phase, which is the most dynamic part. This is where decisions are made within hours or even minutes of events happening on the grid, such as responding to sudden demand spikes, generation drops, or fault in the system. Finally, we have the post-real-time operation phase, which is often overlooked but incredibly important. In this phase, all the data from the actual operation, including what went right and what went wrong, is collected, analyzed, and archived. This might happen over the course of a few days, weeks, or even months. The insights gained here are crucial for improving future planning and real-time decisions. What is important to remember is that the safe and economical operation of the grid, it isn't just about reacting in the moment. It's about understanding how actions and data are connected across time, from long-term planning to real-time execution. And the post-event analysis, or to put it another way, effective power system operation depends on decisions made before, during, and after the event. And each phase builds on the other to ensure the grid remains stable, reliable, and cost-effective. In conclusion, the effective operation of transmission and distribution system relies on a well-coordinated, time-sensitive approach that spans from long-term strategic planning to real-time control and post-event evaluation. Each phase, whether it's planning years ahead or reacting to a sudden disturbance within minutes, plays a critical role in maintaining the stability, reliability, and economic efficiency of the power grid. These four operational timescales are not isolated, rather, they are interconnected layers of decision making that support and inform one another. Long-term plans shape short-term actions, real-time operations validate or challenge those plans, and post-operational analysis helps refine further strategies. By understanding and managing these timescales collectively, grid operators can ensure that electricity supply consistently meets demand, withstands unforeseen disruption, and evolves to accommodate changing technologies and energy sources. In a sense, a modern power system can only function safely and efficiently when it is operated with foresight, responsiveness, and continuous feedback loop built on data and experience.